today we have an interesting lunch and learn. We have Rafal, who's one of our system engineers out of Switzerland, who actually contacted me a couple months ago because he was doing a master's at a school called ETH Zurich, which is one of the best engineering schools in the world, and contacted me about this project that he did. And we all know that there's a lot of interest in machine learning and neural networks, and so we thought it would be a nice way of expanding our global community by having one of our colleagues from Europe, for whom this is Friday afternoon, late afternoon, present this project to us.
All right, Rafal, take it away.
Okay. So good afternoon and good evening, everyone. My name is Rafał Firlejczyk. I've been working as a sales engineer for Zebra in Switzerland. And today I have the honor to present you one implementation of artificial neural network in an embedded system. In January, we could learn already about the artificial neural network theory delivered by Stewart and about its implementation in image classification done by Sergey. This time, I would like to show you the project done last year during my post-diploma studies in ETH Zurich. In this project, I designed an embedded device which recognized the human activity using a simple neural network. So what is the motivation of this presentation apart from learning the new thing? Most implementations today use servers or cloud to perform the calculations. But how about implementing the artificial intelligence in a small embedded or mobile device? Do we need it? Well, sometimes it makes sense to have it done locally if we do not have wireless connection or we want to have it done really fast. This is so-called near sensor analytics. Today, we would have three hardware possibilities to realize this. First, use the microprocessor with floating point unit and perform all calculation on this sequential hardware. However, it is not possible for bigger networks because of computation complexity and memory, but still, it is the best and easiest solution for the small networks. I use exactly this possibility in my project. Second, use the general purpose GPU. With its massive parallel calculation, it is very fast solution. For example, NVIDIA Jetson. However, the power consumption is around 10 watts. What is limiting the implementation for embedded or mobile systems because they are charged from the battery. And third, use the special hardware, ASICs, designed to perform parallel calculation and using special algorithms like binary weights. It could be very interesting for convolutional neural networks used in computer vision projects. Here, as an example, I would like to mention the innovative hardware called YODA-NN with its extremely low power consumption. It was designed last year by Renzo Andri from ETH. So what are the goals of this project? So first point is to adopt the C code of artificial neural network and port it to microcontroller. The second is to build the hardware. The third step is to test and verify how good is in reality the accuracy, and check also what is the cost of this achievement in terms of energy demand. And finally, the goal is to answer the question if such a small embedded system could be used for both training and testing of artificial neural networks. So the project was divided into three phases. In the first phase, the prototype has been designed. Here also I was searching for the suitable source code in C and then porting it into the microcontroller. It also included building the prototype. Tests were also done to check the best position to attach the device on the body. In the second phase, I designed a small PC board of 2 inches diameter using Altium Designer. And PCB was designed as 2 layers only and not 4 layers as usual, so that the design can be reused for the flexible PCB if someone in the future would like to integrate it with the clothes. Soldering and debugging were also done, and the big part, however, was testing the device. I had 6 users carrying the device attached to the upper arm and collecting the data. And phase 3, including putting all the results together for discussion and conclusion, and finally delivering the presentation to the examination committee. So I wanted to build a wearable device which recognizes 5 activity classes like laying, sitting, standing, walking, and running. I was supposed to use the artificial neural network as a classifier, as the brain of our system, and the newest hardware with lowest power consumption. There are, however, some questions to answer. What stages has the process of recognition? What other hardware elements, including sensors, should be used? What features should be extracted from the signal? I wanted to use machine learning approach, but what type of artificial neural network should be used? How many layers, nodes, what parameters, and how to tune it? How to test or measure the system, and finally, how to improve the device. However, before we go into details, let us recall information from last Lunch and Learn about the differences between standard approach and machine learning approach in solving the task. In the standard approach, we would either analyze the signal and then we would write a program which implements known rules or formulas that uses the input and predicts the output. The machine learning approach is different. It lets the algorithm to learn such a program itself, directly from training data. In this case, we will provide the algorithm with the input and output data and force it to learn the program to solve this task. So going back to the first question, what are stages of recognition process? The answer are there are 2 stages: training and testing. In the training phase, we will teach the model of accelerometer by feeding him with a lot of input data and letting him calculate the output. Since we know what the final output really is, we can calculate the error and let the system tune itself to minimize this error. This looks like teaching your child by letting him repeat the new thing over and over again and correcting him when he's wrong and hoping that he will learn finally. This phase may last very long and needs a lot of computation power and memory. In the testing phase, we assume that our model is already tuned good enough to work independently, and we feed the system with data and let it guess the result based on the input data and the model. Important to mention here is that this model can be of lower or higher level. In a low-level model, we could, for example, only recognize that the person is walking, sitting, or standing, etc. In higher models, however, we could recognize more general patterns or contexts of these activities. As an example, let's assume that low-level model classifier detects that the person is sitting for 50 minutes, then is walking 2 minutes, then standing 5 minutes, and then again walking 2 minutes. Based on this data, we can then teach the higher level model that this kind of activity pattern is corresponding to employee office work. The employee is working 50 minutes at his desk, so he's sitting. Then 2 minutes walking to the coffee point, then 5 minutes standing while drinking the coffee with colleagues, and then 2 minutes for walking back to the desk. In other words, we change the perspective of our observation window from 1 second, where we can see only primitive activities like sitting, standing, or walking, to 1 hour to be able to see the context of these primitive activities and classify this 1 hour as office work activity. In my implementation, I have focused only on the lowest model, which is recognizing the basic classes of activities like the 5 mentioned before. We will see that our input signal will need to be processed before we can extract important for us information based on which our neural network will learn and perform the classification. In coming few slides, we will focus on the pre-processing, which is located in the beginning of this chain, here shown in yellow. But first, let us see how is the signal looking like coming out straight from the 3G accelerometer. I have registered here all 5 classes, starting from laying, sitting, standing, walking, and running. The observation window of 40 milliseconds is very short, and we can see that the acceleration signal differs significantly, especially when we move.
Yeah.
Sorry, was it a question? Because I can hear some talk. Okay. Also, amount of the produced data is very significant, and every 40 milliseconds float of data is produced.
No.
But already with setting the observation window to 1 second, we can see that the signal is more averaged and is coming only once per second. With that move, we have reduced the amount of data. This process is called pre-processing and segmentation. Having done this, we can proceed to the next important block called feature extraction. Feature extraction is important because incorrect features can make the classification not accurate or even impossible. The rule of thumb is to find a set of features which are delivering different information. The best is if features are not correlated between each other, so they can bring us maximum information. In our simple case, we anticipate that we will need 3 features giving us the information about static position of the device to distinguish between classes lying, sitting, and standing, and 1 or more features informing us about dynamics of position changes to distinguish between classes. Having said this, I have defined altogether 6 features. 3 static features calculated as mathematical mean value to give us the information about the position of accelerometer in 3 axes, and 3 dynamic features defined as 3 variances, what gives us information about the dynamic of position changes. First 3 features are shown graphically here. We can already see that for the first 3 classes like lying, sitting, and standing, we get enough information to distinguish between them due to change of the position of the device or accelerometer. But walking and running may have, maybe, however, more difficult to distinguish. And that is exactly why we defined another 3 features, variances. We can easily guess that during running, the variance will be much higher than during walking, as seen on this slide. And here, finally, I put all 6 features together, and I give them as well labels, assigning the classes. And this is typical process in so-called supervised learning, where human action is necessary to choose the best features. In a more sophisticated system for unsupervised learning, the system will find features itself without human intervention. So, having done all this preparation work, we can focus on the main subject of this project, implementation of the neural network as a classifier, and it is located in the end phase of the recognition chain. In January Lunch and Learn session, we learned about the neural networks and the best ideas about how to learn and how to remember things are coming from the nature. So we know it is still the area which is unexplored, and we know, however, today that this ability is due to many connections between neurons and the way this ionic discharge travels between neurons. It is not an automated and linear impulse transition between the nodes, but a kind of multi-input non-linear logic which is allowing the impulse to travel from one neuron to another. In our brain, we have about 100 billion of such cells and trillions connections. And remember, 100 billion, it is about the same number as the number of stars in our galaxy. So this idea, but very, very simplified, has been implemented in artificial neural networks, shown here. The input signal, shown as X, also travels from node 1 to node 2. The outcome, shown as Y or Y, depends, however, on weights of nodes, shown here as W, and nonlinear activation function, which is mostly sigmoid function, here shown as a function A. So we will stay humble, very humble in our implementation of this network, and in our network we used 6 input nodes and 6 hidden nodes and 5 output nodes connected in the way shown on this slide. To each connection, a weight is associated. For whole network with 3 layers, we get 2 matrices of weights, one for input, hidden layer connections, and one for hidden output connections. So the artificial network can learn things, and the information about it is stored exactly in these weights. In complex implementations, we may have several hidden layers and hundreds or thousands of nodes in each layer. Here we limited this number to 1 hidden layer because of simplicity of the task which has to be solved and due to hardware limitation. 6 features are connected to the input of the artificial neural network. These features we already know. They are describing the state of the system. Just to remind you, we've chosen 3 static features and 3 dynamic features. And based on this input of 6 features, we are going to train this network to recognize 5 states: laying, sitting, standing, walking, and running. After training, we expect that our network will be able to classify correctly 5 classes based on 6 input features. But how to teach, how to train the network? This is a short summary, what and how we will do it. There are a few basic steps which will be done iteratively to find the minimum error, here defined as a loss. We want that system find such a combination of weights in these matrices which will produce the minimal error called here a loss. So in point 1, we are starting with the random values of matrix, which are close to 0 because we don't know what the correct values are. And then in point 2, we calculate so-called forward propagation. It means we multiply the first sample features by weight of our matrix and then apply the non-linear activation function. It is a pure algebra. Finally, system gets the first result, let's say the first estimation, which is of course not correct because system knows what the result should be, it can calculate the error of this estimation, called here a loss, in point 3. And based on this loss, system corrects these weights in the back propagation points 4 and 5. And then the process starts from point 2 over and over again, hoping that the error will be smaller and smaller. Are you with me? If not, next slide will show graphically how it goes. This slide is showing the loss as a function of number of iterations done in training. When done about 1 million times, we can see that loss is getting very small, close to 0. So our network has minimized the loss. And if the loss is small or close to 0, it means also that the accuracy will be reaching 100%, what is the goal of this exercise. But interesting is also to see the zoomed version of this plot. You can better understand here how the optimization process is working. On this slide, between 2 spikes, there are 1,150 iterations. And we can see that we get the model tuned well quite fast, except these spikes. And these spikes represent switching from class walking to running. There is always one peak, meaning a big loss, a big error. This peak can be justified as follows. The network is tuned to first 4 classes quite correctly, but not to the class running. It is probably because running as a class is so different, has so different features from other classes, that the model needs bigger correction to fit to it. Important, however, is the observation that these spikes are slowly minimized as well. And after about 1 million iteration, the model accommodates to this class as well. Now let's talk about hardware. As a core of our system, I've chosen one of the newest microprocessors on the market, 32-bit Cortex M4 with floating point from Ambiq, from Texas. What is interesting in this product is its very low demand, energy demand, due to its patented sub-threshold technology called SPOT. It can be explained very easy. So having a technology to power the transistors with for example, 0.5 volt instead of 1.8 volt would mean theoretically a power reduction of about 13 times, because energy consumption is almost directly proportional to the square of the applied voltage. Further reduction of the voltage to, let's say, 0.3 volt would lead to, in theory, to almost 36 times power reduction. And this technology allows to work under such low voltage. So this is the architecture of the device I've built with Apollo as a microcontroller and 3D accelerometer ADXL. Additionally, I have built in the harvesting unit with the battery and small solar panel. For communication with TC55, I have added the Bluetooth module, Bluetooth 2. Accelerometer is configured to collect 3 times 100 values per second, and then to send the interrupt to Apollo. And device may work in 2 modes. In one mode, in mode 1, it only collects training data and sends it over Bluetooth to mobile device. And from TC55, data are copied to PC. PC can perform then the training offline. Outcome of this training, there are weights, and they are then copied back to the application on wearable device, and device is ready to work in mode 2, where it collects the data and performs classification. Important, training can be also done direct on the device, but it is limited by the memory and time of calculation. It means for the bigger data set, the training was always done on the PC. These are a few pictures from implementation, starting from upper left, the development board used in the beginning to port the software and to take the first measurements to do a proof of concept. Upper right, the PCB with a few integrated circuits, which will be soldered in the special soldering machine shown lower left, and then the PCB with first I6 integrated circuits being soldered already. Then upper left is the using of the development board as the debugger, and further all elements put apart and then put together and built into small case and then attached to the belt for testing. So here again the system and its elements, including accelerometer, solar panel and battery. Device is connected with the TC55 over Bluetooth for communication. So finally, the device has been built, and we could proceed with testing. The first goal of testing was checking the accuracy as a function of different training data sets. I got a help from 6 different users involved in the testing who carried the device and collected the data while laying, sitting, standing, walking, and running. So every second, the system generated one sample with 6 features. So after 10 minutes, 600 samples were collected of one class. Since we have 5 classes, it means 3,000 samples were collected coming from one user. From this data, I took 1,500 samples for pure training and another 600 just for testing. So having data coming from 6 different users, I was able to mix the training data in the different ways to check how it will influence the accuracy in testing. And I got together 13 cases. Cases 1 to 6, these are cases where there was no mixing of training data, like a reference. For example, the classifier was trained using training data of user 1 and then tested against data of each user including 1, so 1, 2, 3 until 6. Then the classifier was retrained using the training data of user 2 and again tested against all 6 users. And the same was done again for users 3 to 6. Another cases, or 6 of them, are more interesting. Here I have mixed the training data of 5 users. Each user contributed equally with proportion 1/5. And with that training data, I trained the classifier. And then, having this model, this classifier, I tested this classifier against the data of the 6th user, the one whose data was not present in the training data. This experiment was important, and it was important to verify if mixing training data of many users makes the model more robust for accuracy decrease, which I saw by single user model. And last but not least, the case 13. Here I created the training data by mixing data of all users in equal proportion of 1/6. So after training the classifier, I tested it against each user. And this case was important to check if a small addition of training data of one specific user, here 1/6, improves the accuracy by this user. And since cases 7 to 12 did not have this small portion of own training data, we could easily see the difference by comparing these cases. It's a kind of a busy slide, only to show you how many different combinations we tested having 6 users and possibility to test differently trained classifier. You can see that when the classifier, this is the accuracy. So you can see that when the classifier is trained using data of only one user, the accuracy is quite low. When tested on data, when we test on the data of other users. But mixing this data improves this accuracy. Of course, the best accuracy is achieved when the classifier is trained and then tested using data of the same user. But this is not interesting. An important slide is this one, showing the improvement of the accuracy by the user with a different activity profile. It is kind of outlier. We can see that adding just a small part of training data of this user to the training set improved the accuracy dramatically from 72% to 88%. And this let us recommend to add a feature to tune the device by the end user to improve accuracy exactly for this user. So the classifier could be delivered with the default model by the producer, but still the end user could be able to add his part of training data representing his specific way of walking, running, and then rerun the training process. We were also able to redo the training and testing using another type of classifier, so not artificial neural network, but the basic one is naive Bayes. And this training and testing were done on the PC using MATLAB module. And you can see much better result of artificial neural network in comparison to naive Bayes, especially in cases where training and testing was not done by the same user. Another goal of this project was to keep the power consumption of the system as low as possible. The best, of course, would be if we could design the energy-neutral system which harvests enough energy itself to work independently. Let me show you the power management principle of this classifier. So BQ from Texas Instrument is performing a power management. It delivers the voltage for our classifier and also transforms the energy of different harvesters to load the battery. In my case, we had only one harvester, solar panel. These slides show already measured power of the device with connected Bluetooth 2.0. Energy demand is about 90 milliwatts. It's a huge energy demand, mostly due to the Bluetooth 2 module. To check what is the real power needed for the classifier itself, I decided to solder another PCB without the Bluetooth module, just to measure effective power needed for this classifier except the Bluetooth. And here you can see the power measurement of the Apollo itself in testing mode without any elements. The microcontroller is waking up every second to perform the recognition task, and it's going to the deep sleep mode for 97% of its time. Measurement was done on the development board. And this is the same slide, but zoomed in to better see the timings. So active mode takes about 27 milliseconds and starts from copying the data over SPI interface from accelerometer. It consumes about 3 to 4 milliwatts, and after that, power increases to 21 milliwatts for about 10 milliseconds for feature extraction and classifying. That's where the power is needed. Then I did the same power measurement, but on my PCB. So timing looked exactly the same as before. However, power in passive mode or in sleep mode was about 1.2 milliwatt. What was still too high for this system. I assume that the controller did not go to the deep sleep mode as it was designed for. And in the same, this is the same measurement, but zoomed in. You can see almost the same timings as before. Further testing, however, should be done to discover why the system still consumes this 1.2 milliwatt when it was supposed to be in deep sleep mode and consume 100 times less energy. So in the end, again, a kind of a busy slide with 4 power scenarios. First case in blue, it is the power measurement of microcontroller alone, measured on the development board. Second, in green, is the estimation of power with added power of accelerometer. And third, in yellow, is the power measurement of my PCB, but without Bluetooth 2. And fourth, in red, is my complete PCB with Bluetooth. So important message here is the battery life of the build system. So it was measured to be 43 days for my PCB without Bluetooth. In case, however, the system could get into proper deep sleep mode, it would be about 1 year on the single charging of the battery with 500 milliampere hour. The battery life with the Bluetooth module on would be, however, less than 1 day. In calculation, I assume also that a small part of the energy of 40 microjoules can be harvested by the solar panel to compensate a bit for the energy consumption of the system. And finally, a few words about future works. The project can be developed further to achieve lower power in deep sleep mode. I would recommend correcting the design of the PCB to add additional measurement points and jumpers to be able to test energy consumption of different elements separately. Further, we could also recommend implementing the system in the new flexible PCB. Since our PCB was designed already in 2 layers, it could be possible to reuse its design in the new project. This work would open the possibility to integrate the classifier, for example, into materials, fabrics, belts, and so on. And we recommend also that in the future, end user should be engaged in the final tuning to train the classifier to get better accuracy. Moreover, we recommend using the Bluetooth low energy module for further implementation if radio is really needed. And this would significantly reduce the energy demand for wireless communication. So in the end, it's time to sum up and answer the question from the beginning, which was, can we have an artificial intelligence running locally on the mobile device? The answer is yes, it is possible. In less complex classification problems, the classification can be even faster because it will be done locally. Also, training on embedded device is possible, but limited to smaller networks and data sets. Use of more complex networks, for example, convolutional neural networks applied for computer vision, could be a subject of an interesting project. Probably another hardware which implements massively parallel architecture should be evaluated due to the huge computation needs. In the end, I would like to thank to Kobe and Winston who invited me to share this presentation with you, and to all of you for listening to this webinar. Thank you.